Hi, welcome to YouWillUnderstandMath.com. This is the second part of understanding the geometric definition of the limit. In the first part, we looked at this problem, f of x equals x squared minus 1 over x minus 1, and we learned that we had an undefined value of the function when x equals 1, because if you substitute x equals 1 in the denominator, you'll get 0, and gives us an undefined value. But we found out that if we take the limit of this function, if we take the limit of x squared minus 1 over x minus 1, as x approaches 1, we get the value 2. And the reason is we could use the cancellation property because we're not concerned with the value of x at 1, but rather the value of the function as x approaches 1. So we did the scratch work here. As x approaches 1 from the left, meaning to the left of 1 on the number line, we are approaching 2, the outputs are approaching 2. As we approach x equals 1 from the right side, the outputs are approaching 2 as well. You see they're decreasing to 2. Consider this image here where f of x equals x squared minus 1 over x minus 1. It looks like this line, as I noted before, except there's a hole at x equals 1 because when x equals 1, we have an undefined value for f of x. But as we did before, as we found values close to 1, right, for the inputs, we found the outputs were approaching 2. As we create our definition for the geometric representation of the limit, let's look at some new symbols and terminology. Notice I only move 1/100th of a unit to the left and to the right of 1. It's a very small value. Let's call that value delta. In our case, delta will be 0.01 because this is 1/100th of a unit on both sides of the 1. This will be 0.01. I did the same thing for the output 2. 2 is where the function values are approaching as x approaches 1. Okay, on the one hand, we have the x values approaching 1. We're going to let c denote 1. Okay, the x values are approaching c, which is 1, and the outputs are approaching 2, which we'll call L. L will stand for the limit in our definition. So as the x values are approaching the value c equals 1, the outputs are approaching the value L equals 2. Around L, I have a small interval of length 0.01 on either side. If I go below the limit 0.01 units, I'll have 1.99. If I go above the limit of value 2, 0.01 units, I'll have the value 2.01 or 1/100th, just as we did here. Now, these small values don't have to be the same. For example, this distance away from 2 could be larger or smaller, and this distance away from C could be larger or smaller. But let's denote this small interval or this small distance away from the limit by epsilon. Now, how far away did I go from 2? I went 1/100th of a unit away from 2. Let's denote that small value by epsilon. That will be 0.01 as well. As I said, epsilon and delta values could be different, but in this case, they are the same. To recap, we denoted the limit, which was 2 in our case, by L. We denoted the small distance away from L, which is the same on both sides, as epsilon, which is 0.01 in this case. We denoted the value of interest for our inputs. In our case, it was 1 as C. And we denoted the distance away from C on either side by delta. If we substitute the values, for example, if we substitute c instead of 1, we'll have c here. If we substitute f of x for x squared minus 1 over x minus 1, we'll have f of x in the place of this. If we substitute L equals 2, we'll have this. This is our generic formula for the limit. In the next video, we'll complete our derivation for the limit, the geometric representation of the limit. Thank you for watching this video. Please like and or subscribe if you've enjoyed this video.